Okay, hello everybody. Welcome back to our ongoing, now completely virtual Astroseminar series, minus the pizza, which is one of my big beefs. I don't get a free lunch. Um, so it's a pleasure today to welcome Alexie Leauthaud. Uh, Her bio is as follows and is conveniently available on her website in a short form, which I will read out to you. She did her PhD in France. She's French, although I guess it's been quite a while since you've been in France.
It has.
Uh, in 2008 in Marseille at the LAM, the Laboratoire d'Astrophysique, with Jean-Paul Kneb and Olivier Lefebvre, who sadly recently passed away. And then she moved to the US. She was a Chamberlain Fellow at Berkeley National Lab in Berkeley for a number of years and did a second postdoc and transitioned to a faculty member at the Kavli Institute in just outside Tokyo. And then she returned to the US, joining the faculty in Santa Cruz in 2016, where she is now. She's very well known for her work in weak gravitational lensing, particularly galaxy-galaxy lensing, and its many applications for understanding galaxy physics and cosmology, which is what she'll tell us about today.
Thank you so much, Mike, and thank you for the invitation. I really wish I could visit in person, and I just wanted to recall fondly my first visit to Waterloo when I arrived there on the day of the biggest storm in the last couple of years and skid around on the streets in my rental car and finally made it to the department. It was a great deal of fun, and I recall it very fondly and hope to visit again soon, maybe not on a stormy day. So
February's a bad time to come and visit
I
in
know,
person.
I know. I forget when I visited, but it was when Kevin was based in Toronto, but it was sometime in the winter. So I'm going to tell you today about a series of work related to galaxies and their connection with dark matter. And I'm going to tell you both about the connection with cosmology, but also sort of some results related to galaxy formation as well. So sometimes the slides don't advance for random reasons. So I'm going to start this again. Let's try this again. This happens randomly for reasons that I don't understand. It just doesn't advance. Okay, let's try again. Now it does. Okay, so dark matter is the dominant mass component of our universe, and we're particularly interested in the spatial distribution of dark matter and the evolution of this distribution with time. This distribution of dark matter is encoded in the power spectrum, and the power spectrum contains a lot of information about the cosmology of the universe, and it's sort of the prime reason why we seek to constrain this power spectrum. However, when we look at the universe, this is a video that also sometimes works and sometimes doesn't work. Let's try it again. What we really see are the galaxies here on the left. And the galaxies are not the dominant mass component. This is dark matter on the right. You can see that it's much more abundant. And we need to be able to translate the galaxies that we see into the underlying dark matter. This relationship between the two is often called the galaxy halo connection. And understanding this galaxy halo connection allows us to constrain both cosmology. For example, the growth history, there are aspects that we can tackle related to modified gravity, so on and so forth. We also touch on topics related to structure formation. For example, the impact of baryons on the dark matter distribution. We know, for example, that AGN probably eject gas from halos, and by doing so, modify the gravitational potential and change the distribution of dark matter. When we talk about this relationship, we also learn about the formation of galaxies themselves. So how much dark matter is there around any given galaxy? What is the connection between the morphology of a galaxy and its underlying dark matter distribution? So this galaxy halo connection sort of touches on all three topics. Now, To probe this galaxy halo connection, we would like to be able to probe the dark matter component. And it's not trivial to do. One of the main techniques that we use is gravitational lensing. And you know this from Mike, who's also an expert in this field in gravitational lensing. And I'm going to show you a little video just to highlight this technique. So in the absence of any mass in the universe, the light from a distant galaxy will travel in a straight line towards our telescopes. When this light is intercepted by a very massive overdensity, such as a galaxy cluster, the rays are bent according to the laws of general relativity and form these gravitational arcs. So here I'm showing you a strong gravitational arc. This is the light from the distant galaxy that is bent and stretched according to this gravitational lensing effect. Now, this is what we call the strong gravitational lensing regime because the stretching is visible by eye. We can also study this statistically in the regime where the changes in the shapes of galaxies are very small. And when we do so, we call this the weak gravitational lensing regime. And most of my talk, in fact, all of my talk will focus on the weak gravitational lensing regime. Before I tell you a little bit about the weak gravitational lensing, I want to introduce some terminology, especially for the students in the audience. So we think that galaxies live in these big fluffy balls we call dark matter halos. So that's a dark matter halo. Galaxies that live at the center of these dark matter halos are called central galaxies because they live at the center. And then there are also galaxies that orbit around in this dark matter halo, and those are called satellite galaxies. One thing that I'll talk about later I wanted to introduce here is the difference between in situ stars and ex situ stars. In situ stars are stars that are formed within a given galaxy. So stars that are formed in this galaxy in this dark matter halo. And we distinguish those from ex situ stars, which are stars that were formed in a different galaxy that later accreted onto the halo, became a satellite galaxy, orbited around, became tidally stripped, and deposited the stars onto the central galaxy. And those are called ex situ because they were formed elsewhere. And this distinction will become relevant further on. One of the techniques that I specialize in and make a lot of use of is called galaxy-galaxy lensing. And the power of this technique is to probe the dark matter halos around galaxies, or actually any object that you like. You could study clusters, you could study AGN. And how do we do this? So we take a set of galaxies, again, your favorite sample. We consider the distance from this galaxy out to the edge of the halo or beyond, and we make circular annuli around this galaxy. Then in each of these annuli, we measure the shapes of galaxies, and we turn this weak lensing measurement into a figure which is delta sigma versus R. Delta sigma you can think of as probing how much dark matter there is in this dark matter halo. So it's a direct measure of the radial profile of this dark matter distribution. So R will be here on the x-axis. R often goes from a few hundred kpc, just on the outskirts of the galaxy, out to the edge of the halo, maybe a megaparsec, and even beyond. We can probe the dark matter distribution out to very large scales. And then the y-axis here is called delta sigma. And I just want you to know that the amplitude tells us about halo mass. So the higher signal, the red points, live in more massive dark matter halos, and the green points live in less massive dark matter halos. And so that's all you need to know for this talk. I forgot to mention, by the way, feel free to interrupt me if you have questions along the way. Happy to stop and pause while we have the slides up. Also happy to answer questions at the end. So I'm going to go through 4 sections. The fourth one will be very brief. We're going to start with a question that I call lensing is low. Then we'll talk about the relationship between galaxy size and dark matter. Then I'll present some new work that's not published yet about the scatter between galaxies and halos. And finally, I'll introduce a new effort that is starting in March. So I'm going to start with a cosmology application. And this is actually something that I think Waterloo is going to be quite involved in, especially with Will Percival and the DESI survey. And so may not need a lot of introduction, but let me nonetheless give a brief one. So I've already introduced galaxy-galaxy lensing on the left as this technique to probe the dark matter halos of galaxies. On the right, I'm showing the 2-point correlation function of galaxies. So we can take galaxies and measure their excess probability as a function of R, and we call this clustering. It's been known for a long time that the combination of these two measurements is a very powerful cosmological probe. And in particular, what it tells us about are two of the key cosmological parameters, which are omega m, how much dark matter there is in the universe, and sigma 8, how much that dark matter has grown over time. And this combination actually probes S8, so a combination of these two parameters. And we often say that S8 probes the growth history, how much the distribution has grown over time. It also gives us clues about potentially modified gravity. This combination could tell us about dark matter models. And there are also other effects which are often called nuisance parameters, but are interesting in their own right, which are the effects of baryons on the dark matter distribution and assembly bias. I'm not going to go into detail. So a very powerful combination. Now, when BOSS was the primary spectroscopic data set, I worked quite a bit with BOSS. This is going to be now superseded by DESI, which I'll talk about shortly. But let's go back to the BOSS era. So in 2016, I studied the dark matter halos around BOSS galaxies. These are red galaxies, very massive, the most massive galaxies in the universe, located at redshift of about 0.5. And what I did is I said, well, we know this probe combination is really powerful. I'd like to take advantage of this. So I measured the lensing. But unfortunately, I encountered a kerfuffle, which is when I modeled the clustering and predicted what the lensing should look like, the lensing was always low compared to the prediction. In fact, it was low enough that I couldn't run an MCMC chain and get a good fit. So trying to fit these data just gives you a very bad chi-square. You get a bimodal distribution. You can't actually jointly fit the data. If you don't vary cosmology, I should say, by the way. Sorry, forgot that precision. So I ended up publishing this result in 2016, where the observation is that if you take the clustering of BOSS galaxies, make some assumptions about how galaxies live in dark matter halos, we find that it overpredicts the lensing by about 20 to 40%. And this has since been confirmed by a variety of other work, which I've listed here. Some recent work with Johannes Lange that we published looked at this in a different sample. And we also looked at this as a function of radial scale and dark matter halo mass, because our thinking was that if this is a real effect, it would be interesting to understand whether there is a scale dependence or halo mass dependence, because that would perhaps provide some clues as to theoretical models that could explain this. And what I'm basically showing here is that this offset is independent of scale and halo mass. So what could be going on? There's a variety of explanations, which we've sort of gradually been working through. I don't have time today to go in any great detail in all of these, so I'll just point you to the papers if you want to learn more. Modified gravity goes in the right direction, but we found that given constraints, it's generally too small to explain the whole effect. Massive neutrinos also go in the right direction, but again, alone would be too small to explain the full effect. Now, there are two other effects, which again are these, from a cosmology point of view, nuisance parameters. One is the effect of baryons on the dark matter distribution, and the other is assembly bias, which I'm not going to go into detail about what that is. Generally speaking, I found this, and some other people have also found this. These two effects go in the right direction, but are not found to be large enough to explain the full effect. So, one thing could be that maybe multiple things are going on. That's quite possible. Another explanation, which would be the most exciting explanation, would be that this has something to do with cosmology. So I'm just going to give us a few slides on what this would imply for cosmology. I'm showing you here some contour plots of omega m, the amount of dark matter in the distribution, and amount of dark matter in the universe, and sigma 8, the growth of the power spectrum. And I'm showing you the results from the Planck CMB satellite, and then contours showing you in blue what would be needed to match the gravitational lensing that I showed you earlier. And what you can see is that to match the clustering and the lensing, you would need to either bring down omega m or bring down sigma 8. And in a way that takes you away from the Planck distribution. So this would be really exciting because it would be evidence for something very interesting going on in cosmology. So that's what would be needed from the cosmology point of view. This is a figure from Johannes showing what the value of sigma 8 and omega m would be. And on the right-hand side, I'm showing you also the halo mass distributions that we probed here. With this sample, we can probe the range about 10 to the 13 to 10 to the 14. And over this mass range, we found no evidence for any smoking gun, for anything being different in this signal. Also wanted to highlight some recent local work from Waterloo that also studied a similar question from peculiar velocities, and interestingly also coming to similar conclusions with respect to these parameters. What would this mean in terms of the power spectrum? This again comes from Johannes's paper. Blue and red indicate the scales in the power spectrum that would need to be lowered to match the lensing data. Now this is quite interesting because there's overlap here with the range probed by the CMB, and so that puts some constraints, some theoretical constraints on what could be going on here. So I'll leave it at that. Now, there's another effect which we need to pay very serious attention to, which is systematics in the lensing data. Lensing is a very difficult measurement to make. There's a lot of details that need to be taken into account, and systematics are really at the forefront of any modern day lensing analysis. There's a lot of people working on this topic, and a lot of all of the current lensing surveys spend majority of their time thinking about these questions. I would just wanted to highlight an effort that I've been involved in called Lensing Without Borders, which is one attempt to try to quantify these systematic errors. So this is a project that I've been leading in collaboration with Alexie and a number of other people that are highlighted on this slide. And the idea was to say, can we get some empirical constraints on any lensing systematics? Especially in the context of thinking about unknown unknowns. So there are systematics that we know about and we quantify, but we are always concerned about systematics that we don't know about and we haven't thought about. So we developed this methodology as sort of an empirical test of, are there any unknown large effects in the data that we're not aware of? So what we do is we've taken all of the different lensing data sets from HIBA SupremeCam, the Dark Energy Survey, the KID survey, CFH2Lens, CS82, and Sloan. And we're doing a comparison of the lensing amplitude across all of these different surveys. And these amplitudes should agree in the absence of systematic error. And any disagreement we take as a sign of systematic error. So this paper is currently going through collaboration review. So I'm not really supposed to talk about it until that is finished. So next time I come and speak with you all, I hope to be able to show you the results on that. I'll just pause here before I move on to the second section to ask if there's any outstanding questions related to this cosmology application.
I have a quick question, if you don't mind.
Yeah.
Hi, by the way. Yeah, so you didn't talk about assembly bias, and I was just wondering, if you could comment, just because we had a talk yesterday by somebody who talked about this lensing is low problem.
Oh, good, interesting. Okay.
Yeah, saying, basically arguing that if you take into these assembly bias accounts and environmental bias effects, you can account for this discrepancy between the models and the lensing signal. And so I'm just curious about your thoughts on that.
Was that, just out of curiosity, was that Sandy?
Yeah.
Okay, so this paper, I think, highlights the problem. If you, what assembly bias does is it changes the relationship between the 1 and the 2 halo term, is one way of saying it, the amplitude between the small scale lensing and the large scale lensing. And in the initial studies, that 2016 paper that I told you about, we only were able to probe the signal down to small scales because we just didn't have the data to go to larger scales. There you can invoke an assembly bias effect. In this recent work, this has now been pushed out to 50 megaparsecs. And what you see is that the difference is scale independent. You see, this 20 to 30% is pretty much scale independent and halo mass independent. What that means is that it's very hard to invoke an assembly bias signal, especially mainly because of the large scale effect. To try to explain it in a different way, the galaxy clustering is very tightly constrained and imposes a very tight prior on the bias of halos. And on large scales, lensing is just probing the bias, and there's sort of no way around changing this bias. So I still think assembly bias is difficult to explain the signal.
Okay, great, thanks.
I think James also has a question.
Hi, Alexie.
He has it.
Is there any overlap with the Boss sample? I mean, are any of those strong lenses? Like, do you get any leverage from looking at individual strong lenses?
Oh, that's a good question. Yeah, there's definitely strong lenses in here. Let's see. I haven't thought about it in the context of this question. The only thing I would say is that we did do kind of an analysis with Alexandra Sonnenfeld for strong lenses. And we do find we tried to combine the strong lensing and the weak lensing. We do find interesting effects that we, in that context, thought could be related to possibly IMF gradients in the galaxies. But overall, if I go back to this
no one takes IMF variations seriously, surely.
Sorry, well, I'll put you to the paper.
That's just me trying to be provocative and provoke Alexa. So.
All right, that's true. That's true. No, it's a really interesting difference in that paper. I'm happy to send it around if anyone's interesting.
Okay.
But let's look at this distribution. The galaxies that we're looking at primarily probe the halo mass range of Q10 to the 13. And the strong lenses are going to be more over here, I think. They're kind of the tail of that distribution. So beyond saying that they're in a different halo mass regime, I don't have a whole lot extra to say. There haven't been that many comprehensive weak lensing plus strong lensing from a cosmology point of view combinations. So I think it's something that's worth looking into further.
Okay, thanks.
All right, feel free to ask me questions at the end too if anything comes to mind. So I'm going to talk now about a different effect, which is talking about the relationship between galaxy size and dark matter halo mass. So one of the key ingredients in the galaxy halo connection is the relationship between galaxy mass and dark matter halo mass. And this is called the stellar to halo mass relation. One thing we started asking ourselves in my group is, what's the connection between galaxy mass, dark matter mass, and galaxy size? And so we're interested in the question, do the sizes of massive galaxies depend on their dark matter environment? And I want to just underscore here that our work is really focused on the most massive galaxies, mainly because they're the ones that we use for these cosmology surveys, and we wanted to understand this physical connection for these galaxies we use for cosmology. So we set out to study this question with a collaborator called Song Huang. And to do this, we took advantage of some really beautiful data coming from the HyperScreenCam survey. So I'm showing you here some data from the Sloan Digital Sky Survey, and then zooming in to these data collected on the Subaru telescope. And hopefully this illustrates the gain that you get from going from a 2.5 meter to an 8 meter telescope. So you can see two things. One, the data go a lot deeper. This is what we use for the gravitational lensing, by the way. The depth enables us to get a lot of really distant galaxies that we use for shape measurements. But then also, if you notice here, bright galaxies, you can see the outskirts a lot better. So if you look at this galaxy, with the HSC data, you can see this light going out to much larger radii. And so we took advantage of this fact in this work. So this is Song Huang, who's led some really beautiful work on this topic. And I'm showing you here a montage of galaxies from HSC that we have classified according to our measurement of their extended envelope. So massive galaxies are quite diverse. We have in the past tend to think of them as monolithic and self-similar. They are not self-similar. And they have a lot of diversity with respect to their profiles. And I should say I equate profiles with size. So different profile would also mean a different size. Here, for example, is a very compact galaxy. This is a 100 kpc scale. Here is a very extended galaxy. These two galaxies have the same mass in the core, but this one has a very extended envelope. And you can see that if this is a 100 kpc scale, the HSC data allows us to measure this light out to 100 kpc. You can just see that in the image. You don't have to be convinced further. Like, you can see the light out here. That was really unique at the time when this data was collected. There was no other data set that allowed us to go out that far. So we're going to study these profiles, and to simplify these figures, we're summarizing the profiles by two quantities, the mass in the inner part and the total mass going out to 100 kpc. So this is a galaxy profile. This is how many stars there are as a function of radial distance. These are massive galaxies, so they extend from 0 kpc out to 100 kpc and beyond. These are galaxies with masses of 10 to the 11.4 and above. So M100 is going to be the mass within 100 kpc. We choose this because it's where we think we can reliably measure this with HSC. And then M10 is the inner mass of the galaxy, which is the mass within 10 kpc. So to simplify these profiles, I'm going to put galaxies in this plane. It's the plane of M10 and M100. And galaxies spread out in this plane because they're not self-similar. So for example, here, you could have a compact, let's see, this would be a extended galaxy. It would have this value of M10, but would have a lot of outer mass. So an extended galaxy would live over here, and a compact galaxy would live over here. So there's a lot of diversity in these profiles. Right, so compact galaxy, extended galaxy. What we were then able to do with the gravitational lensing was study this entire plane in terms of gravitational lensing and map out the halo mass distribution. So we are making these bins. Give me a second, I'm gonna shut the door because my daughter walked in and opened the door. All right, noise source removed. So these are the bins. And in each of these bins, we're going to study the gravitational lensing, and that is shown on the right-hand side here. So remember when I said bigger amplitude equals bigger halo mass? Just look for changes in amplitude, and then you'll know when the halo mass is bigger. And the beautiful thing about these data is you can see it by eye, so no need for a complicated model. As you step up here, the lensing amplitude goes down, and you can see how the halo mass varies across this plane. So this is actually also indicated by this shaded region where I'm showing massive halos down here and less massive halos down here, going from about 10 to the 12.5 all the way up to 10 to the 14.5 and above. So this is really interesting because it is an indication of a connection between halo mass, galaxy mass, and halo size. And I wanted to also give you some interpretation of this figure. I also wanted to highlight some of your local work here with Mike Hudson, who studied a similar question, and I believe found similar results. I think the results are quite comparable. Basically, what we find is larger envelopes equal larger dark matter halos. And so, I call this the halo mass dependence of the mass size relation. And I want to give some interpretation for why we think this relationship exists. It comes back, I think, to the physical formation of massive galaxies and how they form in what we call the two-step process. So we think that massive galaxies form their inner parts, their cores, their in situ mass at high redshift, redshift 2 and above. And it forms from a lot of gas cooling onto halos during the rapid halo formation phase, and a lot of star formation happening at these early times, also disk instabilities, which lead to a lot of star formation. But then massive galaxies quench for still somewhat mysterious reasons. And so they stop forming their in situ mass. Now, the galaxies quench, but their halos could continue to grow. So you could imagine a scenario where you have one early type galaxy formed in situ mass, then it lived in a quiet halo that didn't grow very much. It would remain a compact galaxy. On the other hand, a different galaxy just could randomly live in a halo that continued to grow since redshift of 1. This growth would increase the halo mass, moving this galaxy over here. That halo growth would bring in satellite galaxies which contribute to the ex situ mass. And so this builds the extended envelopes, growing the extended envelope on the x-axis and also growing the halo mass. So this is what we think the physical mechanism is for creating this plane. And we've tested this in simulations as well and seems to bear this out, but further work could be done on this topic. So I'll pause briefly here if there are any questions on the second section.
I can't remember if from your paper, if you fit either the smaller mass or the larger mass, presumably, I mean, if you turn the problem around and ask yourself, if you just take the larger mass, is there any residual dependence on the smaller, the inner mass? Yeah. Or are they both necessary?
So let me just see whether this answers the question.
Maybe.
I think what you're saying is if I fix the outer mass, so I'm going to go along this plane.
Yeah, so you need both, I guess, looking at that, right?
Oh, do you mean by outer mass, you mean not the total mass, you mean just the outer mass?
Well, I'm trying to wonder if there's a fundamental parameter that when you identify it, all the other correlations go away. That's sort of what I'm headed towards.
Okay, yeah, I don't know.
I mean, we looked at it at a fixed stellar mass, then looking at the size. You're looking at different definitions of the stellar mass. Mm-hmm. Is there one definition which is sort of fundamental? In this plane, I guess you can see, because the lines are diagonal, that both parameters are essential to predict the halo mass.
I think so. And I think the reason is this figure, although it's a little small here, so I apologize. But when you plot these massive galaxies, for example, here, we've done both. You can fix the outer mass and plot the profiles, or fix the inner mass and plot the profiles. And what you see is that there's always a range of profiles. Like you fix the inner part, there's a lot of scatter in the outskirts. So the profiles themselves are not self-similar. There's no way of reducing the profile to like just a sourcing index. That wouldn't be accurate. So the profiles themselves are diverse, and then that connect them, and then those also live in different dark matter halos. So I think the answer would be difficult to summarize it with a single parameter. But we're thinking about further. Does that answer your question, Mike?
Yeah, more or less. Yeah.
Just to follow up on that, so if you show that contour plot again, with the diagonal lines, yeah, this one, I guess, Like, so what's the slope of that line? Like, do you know?
It's in the paper, but I don't remember. I'm happy to dig it out for you.
Like, but it seems that if you go like 0.2 in the x-axis, do you also go up like 0.2 in the y-axis?
A little bit. It's a little bit shallower.
Oh, it's a
So
little bit shallower.
7, yeah. So see, this would be this line. And so it's a little bit shallower than a one-to-one relation.
Okay. So it's not just that you can subtract these two masses or something to get like the...
Yeah.
You know.
I don't think so.
But you could construct a linear combination of those two masses and get your answer, I guess, right?
Yes. And so we actually, in the paper, we have a linear combination of the two masses that supposedly gives you a better tracer of halo mass. That's what we did. So we, you know, if you were to step across in this direction from here to here, you should get a better tracer of halo mass than if you just fix the total mass, for example. And actually that leads into my second part of the talk, because one of the motivations for us doing this was to try to think about reducing the scatter in our tracers with halo mass. From a cosmology perspective, it would be really nice to have a tight relationship to probe halo mass for lots of different reasons. And so by sort of discovering this third variable, you can make a better tracer of halo mass by going in this direction rather than in this direction, which was what most of us do. There are some subtleties there, which I'm not going to go into detail, but I'm happy to talk with you more about it later. But this leads me to the third part of my talk, which is how well do galaxies trace halos? And before I go into that, I want to give a little bit of motivation that relates to the DESI, the Dark Energy Spectroscopic Instrument. So DESI is the first stage 4 experiment underway. It's very exciting. And the goal is to measure the effects of dark energy using the BAO acoustic peak and via the measurement of 30 million galaxies over 14,000 square degrees. It is now underway. We're doing a science verification, getting spectra. It all looks great. And DESI is really exciting. DESI Y1 will be more powerful than BOSS. So we won't have to wait long before we improve on the cosmology constraints from BOSS. Now, one of the topics I'm interested in DESI is galaxy clusters. Clusters are important probes of the growth of structure. Growth of structure is one of the cosmology parameters that is the least well measured. It's a difficult one to measure, and we want to improve measurements of this growth of structure. We'd like to be able to find clusters in DESI over the full 14,000 square degrees using optical imaging. And recently, something that's come to the forefront is the difficulty of doing this with optical imaging and avoiding selection effects. In particular, projection effects have been shown to be important and were a very important caveat to the recent DES cluster paper that came out. So we're sort of hitting the limitations of traditional cluster finding techniques. So we asked ourselves, can we just find central galaxies directly? Because if we can, then we could just identify central galaxies directly, and we wouldn't have to worry about all the satellites and all the red galaxies that live around them that lead to these projection effects. So that was our goal. We're going to use a test that I'm called the top end test, which is a test that we devised to ask, does a given parameter P correlate well with halo mass? So basically what we're trying to do is test different parameters and see which one has the best correlation with halo mass. So I've taken a bunch of objects and I've color coded them by their halo mass, and I'm going to, not with their halo mass, I've color coded them by some property. And I'm going to rank order them. I'm going to select the top N and measure the lensing signal. Another way of saying this is that I'm measuring the lensing signal at fixed number density. Now the amplitude of the lensing signal tells me about halo mass. And if I get a high lensing signal, this tells me that I have a good tracer. If I have a low signal, it means that I have a poor tracer. So let's take a different parameter. Again, I'm going to rank order galaxies by this parameter, select the top N, measure the lensing signal. Then I can look at plots that look like this. So this is amplitude of the lensing signal versus radius. And I've got these 3 different parameters, and one of them gives me a really strong signal. And this one over here in green, for example, I can imagine rank ordering galaxies by the time of night when they got observed. This green parameter is not a very good correlator with halo mass. It just picks out random halos. So you get a low lensing amplitude. And so we've been using this technique to see if we can build better traces of halo mass. And this technique was actually implemented, I think, maybe for the first time in a paper by Renan Barres in 2008. So this is one of the key figures. This hasn't been published yet. We're working on the paper, hoping it will come out soon. This has been led by Christopher Bradshaw, a grad student here at UCSC, and Sung Huang, who's now postdoc at Princeton. And I take a little minute here to dissect this figure. So we're looking at the lensing amplitude versus R. And what we care about here is really just the overall amplitude of the signal. And I'm showing you 3 different measurements. Let's start with this one, the light pink ones down here. You can see that the light pink points are very much below the other 2. This is when you rank order galaxies by their C model magnitude as measured by Sloan. This is the typical catalog quantity for luminosities that you get out of something like a Sloan catalog or an HSC catalog. And for a very long time, we have had the idea that galaxies at the massive end are not very good tracers of halo mass. And I believe the reason we think this is because our catalogs like Sloan have poor luminosity measurements. So the way this luminosity is measured does not actually capture the full light of the galaxy. It's known to be biased and have a lot of scatter. The measurements that we make with SONG in HSC are custom-made measurements that pick out the entire light profile, including the extended envelope. So it's a custom-made measurement that measures the luminosity a lot more accurately. When we measure the luminosity a lot more accurately, we get these blue hexagons. So you can see the lensing amplitude increases. This tells me that when you measure galaxy luminosity properly, you get a much better tracer of halo mass. That's really interesting to me because it means that we can build better traces just by measuring luminosities better. And then the final comparison I want to make is with the red data points. The red data points come from doing the same test when rank ordering galaxies according to what I'm calling the red mapper lambda. So this is what you get when you run a red sequence finder and you build a proxy for halo mass, and that's the parameter called lambda. When you do this, I want to point out 2 things. One is you actually get a similar amplitude to our measurement. And this tells me that just measuring luminosity alone gets you a tracer that is as good as richness, which is kind of mind-boggling. And then the second thing, so I don't have the figure, okay. The second thing is you see a distinct feature here. The red points have this bump. The blue points do not have this bump. This bump, I think, is actually artificial projection effects. If you model this with a simulation using a fully forward model, the shape of the lensing profile for the blue data points matches the expectations really well. Whereas the red ones have this odd feature at about 1 megaparsecs, which I think is a selection effect. So the idea that we are trying to explore is that luminosity measurements allow you to set central galaxies with scatter that is as good as the red sequence cluster finder. This is the scatter in the halo mass at fixed observable. And I want you to look at the red points and the blue points. And the blue points are our luminosity measurements. Red is richness, and you can see that they're equivalent. Whereas a C model magnitude is all the way up here. C model is just bad. You don't want to use C model. Better luminosities get you a really good halo tracer. And then the second thing is that we also think that using the luminosities, you can avoid the projection effects that have started to plague cluster studies and have led to systematic biases in those works. So those are 2 points I wanted to highlight and point you to the paper that we're hoping to finish soon. So a few pictures on this, pictures are worth 1,000 words, as they say. So rank ordering the galaxies by their total mass or their extended light. I'm going to step through the top ones in HSC, and I think you can clearly see that these live in clusters. So this is the galaxy that we're just selecting galaxies by the most massive ones. And you can see that there's a lot of red galaxies around here. This is clearly a cluster environment. For people who haven't studied clusters, it may not be so obvious, but for other people, you can see all the little galaxies around that form the galaxy cluster. So with deep enough imaging, we think we can find central galaxies directly via their extended envelopes. And we want to use this to form sort of like the key component of a cluster finder that we're working on for DESI. This is more of a side note. I'll just mention that we've also done work comparing this with TNG and Illustrious, and we find some cool things, but I'll skip over that. Any questions on this section before I go to the final part, which is very short, so I won't run over time. All right, you can also ask me questions at the end. So the final topic I wanted to introduce is called the Marian survey. And whereas everything else I've talked about has been related to very massive galaxies, primarily because of my sort of biased interest in cosmology, I've been very interested in the very massive ones. This fourth section takes us down to the opposite regime. So the very small, tiny dwarf galaxies. And I'm going to tell you about some new work that we are working on at the moment. So on the left here, I'm showing you, it's a slightly out of date figure, so apologies, I should update it. But the relationship between galaxy mass and halo mass in the low mass regime. So this is stellar mass. Previously, we had been talking about this range up here, the very high mass end. And now I'm going to take you down to this regime, so galaxies with galaxy mass below 10 to the 9. 10 to the 9 is roughly the dividing line where we call galaxies dwarfs, but dwarf galaxies can go all the way down to 10 to the 6 and below. We're going to focus on the high mass end of the dwarf regime, so galaxies with masses between 10 to the 8 and 10 to the 9. And for a long time, and this has been shifting around, there have been some disagreements in this mass regime regarding what you get if you count how many galaxies there are and do this thing called abundance matching, where you try to connect with the dark matter halos just based on the number density, how many there are. And what you get if you measure the rotation curves of galaxies and you try to infer the halo mass from the rotation curves. And there's long been sort of various disagreements in this mass range in particular. There's a lot of things going on down here. One, we think that at the low mass regime, there is a lot of scatter between galaxy properties and halo properties. One reason could be that there's a lot of mass locked up in gas, and so the mass in stars isn't just quite as representative. But also there's a lot of different feedback physics going on that can affect this relationship. Secondly, I think part of these differences are related to the old standing cusp versus core problem. So when we measure the rotation curves of dwarfs in this regime, there's a lot of diversity in those rotation curves, which is related to a diversity in the inner part of the halo profile. Some of these dwarfs have cores, some of them have cusps. There's a lot of variance there. And so when you try to predict a halo mass from a rotation curve, that's quite tricky. So if you mentally go back to the figure I showed of the size of a galaxy and the size of a dark matter halo, you'll realize that the rotation curve, even if you use H1 or a gas component, is really the inner part of the halo. It is not the full halo. And so you're not actually probing the full halo, and there's a lot of assumptions made about extrapolating out to that full radial scale. So the rotation curves only probes about 1/10 of the full halo radius. Okay, so we wanted to maybe help bring some clarity to this regime by measuring the halo masses of dwarfs. Now this is challenging because these are very low mass galaxies. The lensing signal is very weak, And what that means is that we would need many, 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 many dwarf galaxies to make such a measurement. So I started off with sort of first order thing, which is just trying to understand whether statistically we would have the constraining power to do this in an interesting way. So this is a sort of pretty simple paper I put together with some predictions for how well we could do this. So I asked, taking LSST or Raman or HSC, do we have the weak lensing constraining power to measure these halo mass distributions? And I put in the numbers and found that yes, the answer was we do have the constraining power. So following up on that, we designed the Marian survey. I'm collaborating in particular with Jenny Green on this question, as well as a number of other people. And just to say one word on our namesake, we named this after Marian, the first female entomologist from 1647, 1717. And we have her as a namesake because she studied very small things. She studied insects, and we study very small dwarf galaxies. She also had amazing observational skills. She had this crazy idea that observing things could tell you about them. So for example, prior to her work, we thought that butterflies spontaneously were born from pieces of dirt. You had a sod of dirt, and suddenly one day it turned into a butterfly. She took caterpillars and put them in a box and watched them and discovered the metamorphosis of the caterpillar into the butterfly. So we really liked this observational approach. Okay, so what is Marian in 2 words, and then I will wrap up. We have designed 2 custom-made filters created by Asahi that probe the O3 and H-alpha emission lines of dwarfs from about redshift 0.06 to 0.1. And we're going to cover 800 square degrees using 60 nights on the Blanco telescope. We were approved as one of the survey programs starting in March next month. And using these emission lines, we're going to find, we think we'll find about 100,000 dwarfs between 10 to the 8 and 10 to the 9. And we're going to use the Hyper Streamcam survey to measure their dark matter halo masses. I forgot to mention that one of the most difficult thing in this measurement is accurately finding the dwarfs and getting good redshifts for them. So this will give us redshifts good enough to trust that our sample is robust, and will give us a redshift precision of, I forget, but good enough. Okay, so that's happening soon. Next time I come and talk with you, I'll show you results from that. One slide, just to say that on a very different topic, I'm very concerned about the effect of the climate crisis. And I think it's something that we all should be thinking deeply about. And I wanted to point you to Astronomers for Planet Earth, which is a new group formed to unite astronomers around the message of we need to deal with the climate crisis. I will finish there. Thank you very much. Happy to answer questions.
You got some virtual claps there as well as the real one. Okay, thank you, everybody. I would say if you have any questions, maybe best just to blurt them out rather than raise your hand. So go ahead.
Alexie, I had a quick question about part 2.
Mm-hmm.
Did you see, we were talking last week about Peter Beruzi's paper about clustering. So it seemed like for size, he was getting a good match to size if it was correlated with growth rate. So I think that's kind of consistent with what you're saying, that things that grew late are bigger.
Right, yeah.
You're talking about growth rate of individual halos, right?
Yeah.
Not to be confused with the cosmological linear growth rate.
That's right. That's right. He was saying if you tagged things halos based on their growth rate, you got a particular clustering pattern that matched bigger things. Yeah.
No, I think that's very consistent. Modulo the fact that I've just studied the massive regime. Mm-hmm. Things could be completely different in an L-star regime where, you could imagine size being more related to angular momentum of the halo or something. But mm-hmm. in the phase where massive galaxies grow through ex situ growth, I think this is very true.
Mm-hmm.
Good. Alexa, did you have a question? You turned on your camera.
Yeah, so about the Mirian survey. So you said you're going to use HSC to get that, measure the halo masses of all these 100,000 dwarf galaxies you expect to find. But that would just be an average halo mass for all those dwarfs. And so, I mean, I saw in your slide that you made a quick mention of UDG's mass range. And so, but that wouldn't get at the possible effect of there being these overmassive halos or even undermassive halos. Could you just say a little bit more about that?
Yeah, absolutely. Yeah. So we make an average halo mass measurement in a bin. So very much agreed. Now, what we'll find will depend critically on the scatter and this relationship, but I'm showing you here some predictions. If we bin galaxies between 8 and 8.25, 8.75 and 9, with some assumptions about the scatter, the predictions that we find actually different lensing signal. And so you will have to assume something, you have to forward model this based on how much scatter you have, but we should get constraints on the scatter just based on the fact that we can see differences in the amplitudes over this mass range, 10 to the 8, 10 to the 9, yeah.
Okay, great, cool.
Andre?
Hi. I just have if you can maybe expand a bit more on this CMOD bias. So you were mentioning that you should not use I guess the luminosity based on the CMOD. So can you just say if this is like specific for very big galaxies and what kind of bias is that this introduce?
Yeah, absolutely. It's specific to big galaxies. And what's happening is these models are fitting galaxies with a specific model, which is a combination of an exponential and a divocular. But these massive galaxies, if you look at their light profiles, they're actually not well fit by these models. They're not even well fit by a single Sursic, and they're sometimes not well fit by a double Sursic. So I would call this a model bias. We're not fitting the right models to the data. Plus, some of the data sets we are using are not deep enough to actually constrain the outer light, which contains some of the mass. So a combination of model bias and data depth is leading to this measurement error.
But
It's not as bad for L-star galaxies, it's different.
Okay, yeah, okay, thanks.
Christine? Oh, sorry. Somebody else had their hand up before you, but Christine had her hand up?
Yeah,
no?
so
okay.
I'm not very, hello?
Go ahead.
Oh, so I'm not very familiar with halos, but I was wondering if the stellar envelopes question is at all related to like the concentration mass relation where larger halos are also puffier and more extended in general?
Yeah, absolutely. It is definitely connected. I think maybe the question we want to ask is what is the direct, what's the most connected physical property? And I think what's going on is the concentration of the dark matter halo also relates to when the halo formed, whether it formed early or whether it formed late. That changes its concentration. And halos that form late will bring in a lot of satellite galaxies that will add to the outer envelope after the central galaxy has quenched. And so I think there's a connection, but it's an indirect connection in some sense. It's not the concentration that is directly affecting the shape of the galaxy. It's the fact that it lived in a halo that formed earlier or later that happens to have a different concentration. Do you see what I mean?
Yeah, thank you.
Thanks. Ghazal?
Yeah, and follow up on the modeling for luminosity. Why is it very impractical to do a joint fit, like to at the same time improve the models and as well as use them to extract the other information?
Yeah, absolutely. I think it's definitely something we should be considering with our standard pipelines. It has not really been implemented in traditional pipelines. Like I think the LSST pipeline will still get these massive galaxies wrong. It's just person power. Someone needs to put the work in to do these fits properly for massive galaxies. But there's another angle, like for example, the LSST pipeline doesn't fit 3 star 6 to massive galaxies. It's time consuming. But then also there's another question, which is to get the light profile correct, you need to worry a lot about sky subtraction around the massive galaxies. And the traditional data reductions don't deal with that very well. So the best way to do it currently is to go back to the imaging. This is what we do. Deal with the sky subtraction around the massive galaxies, remeasure the profiles. I'll give you an example of decals, the imaging that's used for the DESI survey. Decals actually has really good profile fitting from Dustin, who's in your neck of the woods.
He usually comes to these meetings, but he must have a conflict today.
Oh, there we go. But anyway, so Dustin has done a fantastic job with model fitting in the decals data, but the standard pipeline doesn't do sky subtraction very well. And so we've tested luminosity recovery in decals. You only recover the luminosity properly if you use a custom-made pipeline built by John Moustakis to try to do the sky subtraction with massive galaxies, even after Dustin's, fancy profile fitting. So I think there will be further work done on this that will eventually be included in pipelines, but it's not there currently.
Thank you.
Yeah.
I think we're a little bit over time. We should perhaps switch to thanking Alexie again. So thank you.
Thank you so much.
Interesting and broad talk. Maybe hopefully we can come back again and visit sometime face to face when all this mess is over.